So if you recall, when we were together last time, I had started talking a bit about reactive programming, and we talked about different ways in which reactive programming abides by certain principles, things like resilience and responsiveness, elasticity and message-driven. And now we're going to start talking about Project Reactor, which is the reactive programming framework we're going to focus on in this class. So we're going to talk about several key classes in the Project Reactor API. By far, the most important classes are Flux and ParallelFlux, but we're also going to talk about something called mono. You have to use mono now and again for certain things. So there are three key classes in the Project Reactor API, unlike about a half dozen classes that are important in the context of RxJava. Project Reactor is a little bit later. It came later. They had better chance to think it through, so they didn't have quite as many classes emerge. So we're going to talk first about mono. So mono is a class that has operations that either complete successfully or fail, and therefore either may or may not emit a single value. The emphasis with a mono, as suggested by the name, is one value, mono. This is very much like a Java completable future, or kind of like an async optional, if you recall what an optional does. Here's a very simple example where we have an unreduced fraction, and we're going to go ahead and reduce it in a single thread running in the background. We're going to convert the result to a mixed string, and then we're going to print the results out if all goes well. So that's kind of how a mono works. These classes, all these different reactive classes, can be documented by something called a marble diagram, which you get used to if you look at the documentation. And as you look at the documentation, you'll see marble diagrams all over the place. So let's talk about what a marble diagram is. For a mono, there's a timeline where time flows from left to right. So you can see we're starting here, and it's going to the right. And this is the item that will be emitted at some point by the mono. So it's green initially. And then we're going to have a box that indicates that there's a transformation being applied to this mono by this operator. And the text inside the box indicates the type of transformation. So it would be something like map or flat map or zip or whatever. There's all kinds of things you can do as operators. In fact, there's dozens, if not hundreds, of operators on these classes. This mono here is the result of the operator applying the transformation on the input. The vertical line indicates that everything went well, it succeeded, it produced a result, it's a valid result. But if something goes wrong and the mono terminates abnormally, then that vertical line is replaced by an X. There's a bunch of operators. There are factory method operators for creating monos. There's operators like map and flat map for transforming them. There's so-called action operators, which have side effects, usually things like printing a result or logging a result. There's various operators for concurrency and scheduling. There's operators for combining monos together. In various ways, you can zip them and reduce them and so on. There's suppressing operators that have the strange property of not producing a value, but simply either completing with success or failure. There's some blocking operators, et cetera, et cetera, et cetera. There's lots and lots and lots of mono operators. The next class, which we'll focus on extensively in this course, and you'll need it for all the assignments that relate to reactive streams, is the Flux, which is going to emit an infinite number of events, 0 to infinity, and anything in between. And it may complete successfully, or it may fail. This is very similar to an asynchronous Java stream, where you might use completable futures instead of synchronous code. So it's kind of like combining those two different worlds. Here's an example where we create a flux from a big fraction emitter, which is a way of emitting stuff. We'll talk more about that later. We take only up to a certain number of these big fractions that are emitted, because otherwise it'll go on forever. And then we do some reductions where we're going to reduce and multiply the big fraction in a parallel thread pool. We collect the results of all those reductions and multiplications into a list, and then we go ahead and print the results out. We'll show this in more detail later, of course. One of the other things that a Flux does, which we're going to talk about in more detail shortly, because it's a very important feature of reactive programming and a very necessary feature of reactive programming, is the ability to support backpressure. In this case, the subscriber is going to indicate to publisher or publishers how much data that it can consume in one fell swoop or in one tranche or chunk. So we'll take a look at this in more detail, but here the subscriber says you can send me up to 3 events, and then there's 3 on next calls, at which point the subscriber has to indicate I'm ready for the next chunk, the next tranche. Fluxes can also be documented using marble diagrams. They're a little bit more interesting because there's a sequence of events that are being transformed or filtered. So once again, time flows from left to right. These are the items that are eventually going to be emitted by the flux after being transformed. The dotted lines and this operator indicates what's being applied, which again could be something like map or filter or flat map or whatnot. That's what's indicated inside the box. The elements you see at the bottom are the elements that are the results of the transformation performed by the operator. If everything goes well, we have a vertical bar at the end. If something goes awry, then we have an X. So similar idea. Honestly, sometimes these diagrams are helpful for something like this. They're pretty helpful. They can also be incredibly complicated, but the tricky part is without seeing any visualization, it's even more complicated to understand what these operators do. So we'll get a chance to play around with this stuff in more detail. There are also a wide range of operators for fluxes, just like there are a wide range of operators for monos. Pretty much the same kinds of things in terms of creating fluxes, transforming them, scheduling them in background thread pools, combining things. There's also something called a terminal operator, which is a little different from a flux. We'll talk more about terminal operators. They're very important to understand the overall concept of reactive programming, and some blocking operators. In general, for both monos and fluxes, you don't want to block unless you absolutely have to, because otherwise you miss the whole point of using the asynchronous features of reactive streams. There's a third type of class here called a ParallelFlux, which defines a subset of flux operators that give you a nice, concise way of processing a bunch of elements in parallel. And this is similar to a Java parallel stream in the sense that you have a bunch of things that are processed in parallel, typically in a thread pool. But there are some differences. And if you want to learn about what those differences are, go ahead and take a look at this link, which is a pointer into my ChatGPT account, where I asked ChatGPT to compare and contrast parallel fluxes with parallel streams. And after some tweaking and tuning, which you will not see because I only showed the version that I liked that came out at the end, it came up with some nice explanations. Good luck trying to find these explanations anywhere else on the web. They simply don't exist. I don't think that there are really any articles that talk about parallel fluxes and parallel streams and compare and contrast them in a coherent way. So this is a nice example of using LLMs if you apply the appropriate prompt engineering magic to get them to do your bidding accurately. So that's the end of the understanding of some of the key classes in the Project Reactor API. You will get a lot of chance to play around with these things by the time we're done with the next upcoming assignments.